Welcome to my Physics 2212 Lab 2 Charge Tape Revisited. So here's a brief table of contents. Now, what is the purpose of this lab? This lab is to fill the following. Create an experimental model where the tape becomes charged and exhibits electric force interactions. And that's what we did in Lab 1. And now we're going to create a corresponding computational model to compare experimental data, this time treating the tape as a line charge rather than a point. So it's a little different from last time, but mostly about the same. These, when accomplished, will demonstrate the following physics principles. Newton's second law, force of gravity, electric force. None of those are new. But the one new principle is superposition. So what are these underlying physics principles? The first one is Newton's second law, which states that the F net is equal to the change of momentum over the change in time. Since our tapes are at rest here, then F net equals 0. Now, our next principle is going to be force of gravity, which near the surface of the Earth, which our tape is close to the surface of the Earth, unless if you went up to the ISS to do this experiment, you're going to have F equals mg. And then electric force, or Coulomb's law. Electric force is applied by electrically charged molecules, in this case the tape. You can do F equals QE. That's what we're going to be using today. And then the new principle, which was not on the last lab, is superposition, in which a charged object is divided into segments, and their E fields are summed to find E net. And we're going to find that that's a little more accurate than treating everything like a point. So our system surroundings and preview findings are that our system is tape B, surroundings are tape A and Earth, nothing novel here, it's the same. But our free body diagram on the right is a little different. You can see that there are multiple charges rather than one, and force of electricity is from multiple point charges. In our computational model, we'll be using n equals 100. And then a preview of our experimental findings are that Fg equals negative mg, is equal to negative 7.742 times 10 to the negative 5 newtons. And because it's our experimental findings, then Fe is found by taking the negative Fg, which is just the same thing in the positive y direction. And then a preview of our computational findings are using superposition, we find Q equals 7.135 times 10 to the negative 9 coulombs, and that's the charge on one tape. And the computational model calculated the magnitude of the force of gravity is 7.499 times 10 to the negative 5 newtons, which is almost exactly the same as experimental findings. And the magnitude of Fe to be 7.188 times 10 to the negative 5 newtons, which is a little different, but still just decimal places off. So almost the same, but a little different. We'll go over possible sources of error later. So experimental procedure, don't want to harp on this too much because you guys are all familiar. We made some U tape, held tape A under tape B, and tape B should have moved up. The distance is going to be the distance between A and B at the point which B moved, and then that measurement is shown in the bottom left. And then we also, from last lab, know that the charge U tape has a positive charge. So for experimental calculations, we have some initial conditions at the top, and we know Fe equals negative Fg equals 7.742 times 10 to the negative 5 newtons from the preview. But to solve for the charge of the tape Q, we will use the following formula for electric field of a rod, which is a little different from what we did last time. And so we also know that Q is the same in both tapes. And so if we want to find the force of a rod instead of electric field, then of course we're going to multiply by Q. That's the F equals QE formula. But since the Q is the same in both tapes, then we can use Q squared and then solve for Q, and that's going to be the charge on one tape. So in this case, Q is 7.135 times 10 to the negative 9 coulombs. And you can see my work in the bottom right there. And that should also answer question 1 from the lab document. So going over our computational model real quick. We have some constants on the left there. We have UF, PHYS, G, Q, tape length, distance. Nothing too crazy. The Q was calculated on the previous slide and carried over into our experimental model, or our computational model. And then in the bottom left, you can see the formula for E field. And in the top right, you can see, let me move my recording right quick. You can see the formula we used to create the line of charges. And then in the center, then that just shows a few things that I had to change in order to get the top tape and bottom tape to calibrate correctly. So the line charge of the top tape, I set the y coordinate as the distance, which makes sense because it's the distance between the top tape and the bottom tape, with the bottom tape being at 0. And then for the axis vectors, then in the x direction, which is the direction we're drawing the line charges, then I put the tape length there, which is 0.39. We should know that from our tape length on the left. That's a constant. And then, as I said earlier, then n is 100 in these experiments. Or in this computation. One second, there we go, perfect. And then we have E scale. I chose 8E equals negative 6. You definitely could have used something else, but that's just what looked best on my model. And then I plugged in Fe scale and then had to do a few calculations at the bottom. You can see that's just me setting up the Q value that we're going to get at the end. And boom, look at that. We have magnitude of electric force, magnitude of gravitational force, and the magnitude of charge on one tape. All of those at the bottom. And you can see our beautiful green arrows on the right with the white arrow indicating force of electricity and yellow arrow representing overall force of gravity. And then all the little green arrows are charges on the line. So it looks pretty nice. Anyways. Discussion and possible errors. The computational model is very close to our experimental results, but not quite the same. We can infer, however, that the forces of gravity and electricity are approximately equal and opposite, which makes sense given our understanding of physics principles. So the computational model wasn't perfect. You can see the magnitude of electric force of 7.187 times 10 to the negative 5, whereas gravitational force of 7.75 times 10 to the negative 5. But that's a 0.6 difference. Those are the same order of magnitude, so they can be estimated to be roughly the same, although I'm sure we could iron out some details if we were to do this lab again. So some assumptions we made is we assumed there were only two forces, electricity and gravity, acting upon the tape. We also assumed tape A and B to be equally distributed line charges. And so, if when we ripped the tape off, one part of the tape became more charged than the other, that would obviously have a different outcome, but we assumed they were equal. And then some possible errors that we could have made are that handling may have returned some electrons to the tape in the process of experimental setup. So, if while we're putting tape A underneath tape B, we touch either one, we could return some electrons to the tape, which would be a little problematic. And then tapes A and B might have had different charges from one another. We assumed Q top was equal to Q bottom, or there might have been an uneven distribution of charge across their lengths, so one side might be more positive than the other, or one tape might have a greater overall positive charge. We assumed that Q equals Q when we calculated the charge on one tape because we used Q squared, and if they were different, we wouldn't be able to do that. So that is a possible error we made. And then we may have needed to use n is greater than 100, or we possibly made an incorrect estimation of mass. I know the greater point or the greater number of charges you use on a line, then the more or the closer you get to your accurate answer. So we might have had a more precise answer if we had used an n greater than 100. And my estimation of mass was just rather low, so I might have done some math wrong there. I don't think so, but it's always possible that I made a calculation error. So questions raised by this lab: what if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to reduce a point charge model to the value you got with your line charge model. So as given in the previous findings, Fg equals negative mg equals negative 7.742 times 10 to the negative 5 newtons, and that's equal to negative Fe. So that means Fe is equal to the positive y equal in magnitude newtons to the force of gravity. That's when you consider the tapes as point charges. Whereas Fg equals 7.499 times 10 to the negative 5 newtons, and magnitude of Fe equals 7.188 times 10 to the negative 5 newtons when considering them as line charges. You can see those aren't exactly equal, which indicates that error was probably made at some point, but they are pretty close, and we can assume they're approximately equal. So why do these estimates differ? Which value is more likely to be closer to the real value, and why? Well, the two models vary in how electric field is calculated. Line charges regard the tapes as rods, whereas point charges regard them as points. Because the tapes have far more in common geometrically with rods, that would be the more accurate model, as electrons were removed from the full length of the tape rather than all being removed at one location. I hope you learned a little bit about physics, and I'll see you on the next one. Bye.